In this video, we're going to take a look at the next section in Unit 2, Chapter 7 on quadratic functions. We're going to be taking a look at Section 7.6, quadratic functions in the vertex form. Now, the objective of what we want to do is to make sure that you can identify a quadratic function and that you know how to graph it when it is presented to you in vertex form. Now, as you go through, you need to be watching for some vocabulary. Please watch for vertex, axis of symmetry, maximum, minimum, domain, and range. Please make sure that you take note of these terms in your notes and that you watch for their definitions as we work our way through this lesson. Now, to begin with, we have this really amazing photo of a dolphin leaping out of the water into the air. And I think most of us would be able to imagine what the actual curve would look like if it were in motion for us. If we were to follow my mouse, you would see that it's making a curve that goes something like this. Now, we call that a parabola in mathematics. And the function which forms a parabola is called a quadratic function. So the question I have for you, and I hope that you'll be able to answer by the time we finish this lesson, is what would you need to know to be able to create a quadratic function that describes this dolphin jumping in the air? So if I were to say to you, all right, I want you to create a math equation that describes what this dolphin is doing, what would you need to know? Well, hopefully by the end of this lesson, you will be able to answer that question relatively easily. First, let me just remind you of the function that you know already, this one. Now you can see it straight in front of you. It's a linear function. We call it linear because it is a line. And if I were to ask you how would you form the equation of this function, most of you would be able to jump in and tell me that as long as you knew what the y-intercept was and what this positive slope actually was, you'd be able to give me the equation of this function. For instance, if this were 2 and the slope is up 1 and over 1, we would have that y is equal to x plus 2. So it's no trouble at all by looking at this, once we realize it's a line, to actually give an equation that describes this line. Well, we're going to be taking a look at this function today. And this shape is what we call in mathematics a parabola. And we call this function a quadratic function. Now, there are a few vocabulary terms that you need to be comfortable with when you talk about quadratic functions. So please make sure that you make note of this, draw the diagram, and put these labels on. The line that goes straight down through the center of a parabola or the quadratic function is called the axis of symmetry. And usually we identify the axis of symmetry by an equation that would create this line. X is equal to about 0.4. So the equation of this axis of symmetry would be x is equal to 0.4. And one thing we should know about it is that whatever we see on either side, if I look at this point on one side and that point on the other, they are exactly the same distance away from the axis of symmetry. Next, we have a point at the very bottom, in this case, of our parabola. We call this the vertex. And technically speaking, this is the spot where the graph changes directions. If you could imagine yourself a little tiny insect traveling along, the function is decreasing until it gets to the vertex, and then it begins to increase as you climb back up on the other side. So we say that the vertex is the spot where the graph changes from increasing to decreasing. In this case, if we were to name it, we would say, well, it went over about 0.4 and down about negative 2.3. And our vertex then is 0.4 comma negative 2.3. Now, of course, we can have our quadratic function in two different directions. We say that this one opens up and that this one opens down. We'll look at in a few minutes what makes this happen. But first of all, what I want you to notice is that the vertex on this one is what we call a minimum value. It's the lowest that the graph goes, whereas this one is a maximum value. It's the highest. The vertex is the highest. And usually the way we say it is this. We say that it has a minimum of negative 2.3 when x is 0.4. over here. It's a maximum of 4 when x is -2. All right, so now let's talk about the domain of this function. Now, we realized when we were working in class together that you needed some help with what the domain was. So we talked about how domain is where the function exists along the x-axis, as if we were a tiny little insect walking along the x-axis through here and looking up and checking to see if the function exists. Now, this function, of course, if there are no dots on the top of it, it means it keeps on going. So that line will just keep on going way up, way past my computer, and this one way past. So no matter where I am walking along this x-axis, my function exists. In this case, it's above me. No matter how high above me it is, it's still there. So the question is, how do I write that? Well, there are two styles of notation. One is what we call set notation, where we use the curly bracket and we say the domain, and I guess I should put back here that domain is equal to, and it is all x's such that x is an element of the real numbers. And that just means that it exists everywhere. And we close our curly bracket and we're done. This is what we call set notation. Now we can also use something called interval notation, which shows how the function sort of spans the interval of space across the x-axis. And what we use is we say that it starts at -infinity and it keeps on going all the way to infinity. So we say that its domain is from -infinity to infinity, meaning everywhere. Okay, let's take a look at the next one. And you can imagine what we're doing with the next one. It will be, what about the range? Well, the range is where the function exists along the y-axis. And so we look up and down and say, okay, well, if I start down here at -infinity and travel upward, there's no function. It doesn't actually start until y is equal to 0, and then it keeps on going. So the question is, how do I write those? Now, give me just a moment and I'll put that into our text and then we'll talk about it. Okay, so here you have the way in which we would write the range. We would say the range is equal to all the y's such that y is greater than or equal to 0 and y is an element of the real numbers. This is what we call set notation. For the interval notation, because it actually started at 0 and was equal to it, you'll notice I'm using a square bracket. This shows that it's equal. And it starts at 0, but then it goes on infinitely towards the right. And so I use a rounded bracket because there's no exact beginning or end to infinity. And so my interval notation for the range is the following: square bracket 0, comma, infinity. Okay, so let's take a look then, and let's move on back into our presentation so we can take a look at our question. So the next important thing that we have is, what is the equation of this function? Well, we stopped to consider it for a minute so that we could check out what it was. And we realized we had some values here where we had -1 and 1, -2 and 4, 0 and 0, 1 and 1, 2 and 4. And when we stopped to examine it, we realized that the equation is y is equal to x squared. And what that means is whenever we see an equation that has x to the power of 2 as its highest exponent, we know that it's going to create a parabolic shape, because it's called the quadratic function. So what we need to look at then with the rest of what we have in this lesson is, what happens when we start to play with the equation a little bit. So if I take y is equal to x squared and I just randomly add a 3 or subtract a 5. So what I've done is I've put it in Desmos and I've graphed it over on the side. You'll see the red one is the ordinary one, the blue is where I added 3, and the green is where I subtracted 5. Here's my ordinary one in red. When I added 3, you'll notice that the vertex went up 1, 2, 3. When I subtracted 5, you'll notice the vertex went down 5. 1, 2, 3, 4, 5. So when I add a number or subtract a number on the end, it's actually a very simple translation of this graph. It simply moves it up or down. And the way we write this is by using the following notes. If I just add a number like a q on the end, then that takes my graph of y is equal to x squared and moves it up and down by the value of q. Next, if I take a number and put it inside with the x, if I add a 3 and subtract a 5, let's take a look at what happens. So my ordinary one is the one in red. Now, when I added a 3, the blue one, it went to the left 3. 1, 2, 3. And when I used the green one, subtracting by 5, it went to the right 5. 1, 2, 3, 4, 5. In other words, it seems like when I put a number inside here, it's moving the graph left or right in the opposite direction I would have predicted. So we say this like this. If I put a number inside and let's say it's negative p, when I pull it outside, please notice that it's positive p and that it's moving my point left and right. And in fact, it's moving the vertex left and right. So that leads us to the question where we should be able to answer right away. If we think about what's happening in this equation, I'm going to the right p and I'm going up q, which means that the actual new vertex would just be p and q. I often say that finding the vertex is as easy as picking apples off a tree. And in fact, that is why we call this format, this style of writing the quadratic equation, we call it the vertex form because it's so easy to pull off the vertex from the equation that we see. Now, let's take a look at these ones because there's one more place where I can add some numbers right in front of the x squared. You'll notice I added a negative, a 3, and a 1/3. Let's look at what happens. So the original is the red. Now, when I put just a negative, it flipped the graph over the x-axis. We say it reflects the graph in the x-axis. When I look at the one where I put a 3, if I look at my graph, it's the green one, it's getting taller faster. It's as if someone up here was pulling on a string and pulling it up tighter so that it would rise 3 times as fast. When I take a look at the one where I had a fraction of 1/3, I realized that the arms were pushed open a little bit more. They're not going as high as quickly as the original one was. By the way, the actual official name for this green one is to be vertically stretched. And for the purple one, it's to be vertically compressed. But you will study that more in pre-calc 12. So for now, you could say that when there's a number that's bigger than 1, like a 3 or a 4 or a 5, that it gets more narrow, and that when you use a fraction, it gets wider. So let's sum it all up. If I put a number in front of the x squared, then I know that my graph will be reflected when a is less than 1. In other words, when it is a negative. When a is greater than 1, I know that my graph will be pulled upward, so it will get higher, faster, vertically stretched. And when the a is between a 0 and a 1, in other words, when it is a fraction, then it's vertically compressed. It's pressed down. It becomes wider. Okay, so let's try 2 examples of questions like the ones you're going to see in your homework. Now, once again, I'm just going to pop out so that I can begin to write on this one a little bit. Now, if I look at this one, first of all, let's just talk about what we see. The 1/3. That means that my graph's arms are going to be pushed down. We call that vertically compressed. It's going to open a little wider than it usually does. I can see that it has a +3. So I know when it's inside with the x that it will move left and right in the opposite direction. So it's going to move left 3. And the -1 means it will move down 1. Now, if I think about what that means, I should be able to come up with the vertex fairly easily. In fact, let me just get ready to put a dot in here so that I can actually do it. So if I think about what my vertex is, it's going to move left 3 and down 1. So it's going to go 1, 2, 3, and down 1. So my vertex is sitting right there, which looks great. Now, that was the first thing then, and usually what I do is I actually write it in so that I show that I know what it is. It's -3 and it's -1 for my vertex. So we're good. Now, the next thing we want to do is to draw the line of symmetry. Oh, I just realized that I lost my drawing, so I'll go back to this one. I want to draw a line of symmetry for the next part. So I will create a line of symmetry. Maybe I'll use a different color, but I do need to go back to making it slightly smaller again. And so I need to draw the axis of symmetry. It goes straight down through here with a dotted line. You can see it coming slowly. And remember that this guy will be that x is equal to -3. So when I write this one, I will put that x equals -3 so that I know my axis of symmetry is -3. Okay, now the next thing I'm going to do is I need to find at least one point. Finding one point on the graph, and one of the points that's quite easy to find actually is the y-intercept. Now, if you think about it, the y-intercept is the place where x is equal to 0. And so what I'll do is plug in an x equal to 0 and try and calculate what my number is. All right, so what I've done here is I have substituted in that x is a 0 because I want to find the y-intercept. So I put it in right here as a 0. Now I have to follow the order of operations. First of all, I need to do the bracket. So 0 plus 3 is 3. Next order of operations, I need to do the exponent, and 3 squared is 9. Next one is the multiplication. 1 over 3 times 9 is 3. And I finally can take care of this -1, and so my answer is 2. Now, in other words, what I've just found as I look at this guy is that I have found the y-intercept. And so I should be able to put it right in here. My y-intercept then is 0, 2. Now, it says in the instructions that after you have found the y-intercept that you also need to do the opposite point. Now, what I mean by that is somewhere across here on the opposite side of the line of symmetry is a point. So I always like you to stop and figure out, what is that point? Well, it was 3 units away this way, so it's 3 units away that way. So if I look at what it is, it should be a -6, 2 at the same height that it was for the others. So finally, I have enough points in place, at least at this point, for what I'm looking for. I have enough points in place that I can draw my graph, and so I do my best to draw a quadratic. It's a little hard, especially with this thing. There I go. There you have it. Not a very beautiful parabola, but it gives you an idea of what it is that we look for when we ask you to sketch a graph. Good. Now there you have it. Let's go on then. And what we're going to do is take a look at the very same question. It's the same, and anyway, it's the same function, but they're asking us different questions. They want us to know, what is the vertex? What is the axis of symmetry? Is it a maximum or a minimum? And lastly, what is the domain and the range? So let's use our picture back here to help us answer those questions. Okay, the first couple are pretty simple. What is the vertex? The vertex is -3, -1. What is the axis of symmetry? X is equal to -3. Now, it also asked us, was this a maximum or a minimum? Well, this one comes down and then it goes back up, so it doesn't get any lower. So it is a minimum of -1 when x is -3. The next one says, what's the domain? Well, for this one, the domain would stretch from -infinity to +infinity, or it would be x is an element of all the real numbers. And then if I take a look at the range, I would see that if I consider it from the bottom up, the function does not start until -1. So y is greater than or equal to -1. And we could also write it with the square or the interval notation. And we would put a square bracket. I'll write this one down so you can see it. And you'd write -1, and it would go on forever and ever. And that, by the way, just let me clarify that as I put it in here, is what the range would be in interval notation. All right, everybody. That is a quick peek at some of the work that you're going to need to be able to do for your homework assignment. Please check in Google Classroom, and you will find that there are some questions from 7.6 that you can work on to practice the work that you see. Good luck, everyone.